All right, so today we're going to start off by just finishing the first set of lecture slides from last week, and that is about the concept of what groups are. So this is a very general mathematical construct based on 4 definitions, or the ability to perform 4, or the way they these mathematical entities interact with a particular operation, and the operation itself is left general, the entities themselves are left general, and so you always have to kind of think through whether or not some definition of a set of numbers with an operation is a group. Okay, seems very abstract, but it turns out the reason we want to do this in maths is because there are a lot of cool properties and cool theorems that you can prove based on just the fact that something is a group. Okay, so that's largely what a lot of, at least more like postgraduate maths is aiming to do, is try and define these very broad general concepts so that we can make as kind of sweeping claims as possible. And groups is one of them, and in our case, you know, that we will at least care about showing that some things are groups, and we'll come to that in a minute. But in general, the main reason we care is because vector spaces are an example of a group. And so this is us now building towards a more formal definition of a vector space. Okay, so to start off with, a group will be defined as, say, let G be a set. So a set is any collection of numbers. And this kind of operation-y thing, define however you want, but I'll just call it cross. So you have cross over there. Cross over there. That is called an operator. And this operator takes in 2 elements of the set G, okay, and maps back onto G. That's the whole point of the starting point of this, is that it's going to always map back onto G. If it doesn't map back onto G, then it's not a group, okay? And this here is called the cross product, meaning that we can take any number from G and any other number from G, and then it'll still work, okay? So that immediately restricts us, and we will denote it as like this. So you always just have to be a little bit careful of the fact that this is like a squiggly written G, that is the set itself, whereas if you have the kind of more bold angular font, then it's the set plus an operation defined on it. I'm not going to really play a game or anything too much with the letters and the fonts, but just while you're reading the slides, it's a little bit more important. Okay, so if we have a set and we've defined some operation on it, then it is a group if it satisfies these 4 constraints, all right? So it's not just a group. This bit here does not make it a group. It makes it a group if the first property holds, which is closure, which is kind of what I just described up here with that, which is to say, if I take any 2 elements of G, all right, so for all X and Y in G, whenever I apply the operation, this kind of like operator, this cross operator onto X and Y, I must get back another element of G, okay? We can never leave the set. So if I have 2 numbers anywhere in this set, and it's squiggly G, however you want to draw it, I must then have my operator map back onto the exact same point. So I suppose the better way to draw this then is, it must map back onto another point in G. Okay, it doesn't have to be anything related to the 2 original points, but it must be within that set. It must be something that we could have chosen to begin with. And I'll show you examples now, but let's just get the weird definition out of the way. I'll make this bigger. Yes. Cool. All right, the second one is called associativity. So that says for any 3 numbers from my set G, I can apply the operator first on X and Y and then on Z. So again, my brackets are doing my order of operations here. Or I can apply the operator first on Y and Z, get a new value, and then apply that new value with X with the same operator. We covered that last week. It's called associativity. So whether or not go X, Y, Z, or Z, Y, X, reading back to front or forward to back, the operator will still come to the same value. Okay, there are ways when this just won't work. And again, you'll maybe come across some examples in your tutorials in particular. Then the third case is a neutral element. So there must be an element that is within our set that we can choose from, that when I apply the operator with another value and this E identity, it keeps the value the same, and it can happen from the left or the right. Okay, so this constraint of the identity element always mapping back to x being left or right, that doesn't have to be general. We don't have to have that being the same as that. But if we have the identity element, then we do. Okay, so that needs to hold. Okay, and then lastly, we need to have an inverse element, which says that given that I have picked my my identity element, for every x that I can pick in G, there must be some other y, at least one of them, that will map me back onto the identity. Okay, so the most common version of this that you know of is just inverse, right? So you can see at the bottom here, we often denote it with x inverse. Okay, so if I give you a real number, okay, so let's say we're looking at the set of reals and my operator is multiplication, right? Then in this case, if I take any two real numbers, all right, x and y, and I multiply them together, do I get another real number? You do. Okay, so we have closure. If I take any two real or any three real numbers, right, x, y, z, if I first go x times y, get a new real number, multiply by z, will that be the same as if I first go y and z, get a new number, multiply by x? There we go. Yes. All right, so we're all happy. What is the identity element for this group? What is the element of the real numbers that when I multiply any other number by it, that number stays the same? There we go. And then lastly, we now have the inverse element, which is to say for every value I can pick x in the real numbers, what is another number, or does there always exist another number that I can multiply x by such that I get back to 1? Okay, and it's just 1 over x. Okay, often denoted as that. That's not going to be generally true. That is probably the hardest one to prove. A lot of operations are not invertible, and a lot of sets also will kind of take you. A lot of sets themselves just can't really have inverses defined on them properly. Okay, so that then is the kind of, I think the easiest example of a group is the real numbers with multiplication, but there are many, and it's helpful if we can be able to at least prove these things. So if you wanted to actually prove these points, you would do what I just did with you now, right? You would say let x and y be elements of the real. If I multiply it together, I know I'll get another real value out, right? But you always want to try and be finding a contradiction, okay? If that's like the easiest way to start to prove that something is not a group. If I say to you, prove that, you know, this set plus operator is not a group, what you're going to do is you're going to try and find a contradiction in this. So a nice one to do that with is to pick values x, y, z, and then show that it is not the same regardless of whether I group it that way or x, y, z, and I group it that way first. Okay? That's how you would then contradict this. Yeah.
So you said you take a set of real numbers. Multiplication forms a group.
Yes.
No, I doubt, because if we take 0, 0 does not have an index.
Yeah, that's a good point. So it doesn't form a group. There you go. Contradiction. So do what he just did to me now, and you'll get a group. And you'll prove that it's not a group. And you can see that it's subtle, right? So there obviously is one contradiction there, which makes it not a group, but everything else. So then if we, we could then obviously go not 0 with multiplication. Now that's a group. Okay? Yeah, nicely done, dude. Okay, let's look at some other examples quickly and see how it goes. Okay, there is one more case for this, which is special group. It's called an abelian group, and that is the case where we now have the ordering of operations can be flipped. Okay, again, we spoke about commutativity last week, and that is when you can commute the elements of the set with the operator, you'll then have an abelian group. Cool. So some examples, some other examples. The set of integers with addition is an abelian group. Okay, so if I take two integers and I add them together, do I get another integer? Cool. If I take three integers and I add them together in whatever order, will I still get to the same answer? Yeah. what's the identity element in the integers? 0. There we go. And then if I have any value of the integers, what do I add back to it such that I get to the 0 element? There we go. Okay, and that's all you have to do to prove it. Again, you need to kind of keep your wits about you and like make sure you're considering all the edge cases, and that's where things get a little bit difficult. But also, when I'm going to be marking these things, usually what we'll do is we put one mark on stating the property, we put another mark on proving whether or not it holds or doesn't hold. And so, like, you know, if you forget one edge case, you usually lose one mark. All right, it's not something to be terribly frightened of, but getting like 4 marks in these questions does tend to be take a little bit of thinking. Okay. Does anyone want to tell me why the natural numbers with 0 is not a group? Yeah. There we go. It doesn't have an inverse. And then lastly, the set of n by n square matrices, where dot product is the normal matrix multiplication as defined earlier in the lecture. Is there any? Is this a group, or why is this not a group? There you go. Yeah. What? Matrix multiplication is associative. Yeah.
I think it is a group, but maybe not an abelian group.
Okay. Anyone else have any ideas? Yeah.
So if the determinant is not restricted to 0, will it always be impossible?
Exactly. You need to restrict it to the set of matrices that have non-singular determinants. So in that case, we haven't. So it's not a group. So you won't always be able to invert every n by n matrix. If I then said to you that it is the set of n by n matrices that I know are not singular, then you do get a group, and that is a special group. It's called the general linear group. And now that is a group, but it is not an abelian group. Reason being, matrix multiplication is not commutative.
The second point, what's the meaning of natural numbers meaning of 0? Are we subtracting 0 or?
No, yeah. So this is the union of a set. So if I have a set, let's say, let's draw that bigger. I have a space of numbers. That's one set of numbers A. This is another set of numbers B. When I go A union B, then it's this space here. It's all the space covered by both sets together. Okay. So in this case, when I say natural numbers union 0, it's all natural numbers is all the numbers going 1, 2, up to infinity, whatever. And then now I've added in 0 on the end. Okay. Natural numbers being including or not including 0 is, I guess, somewhat debatable, but for the purpose of this class, you can use natural numbers excluding 0. We're all happy? Cool. Seems like you guys do have the hang of group stuff. Okay. So then now we can look at what this means for something that's a little bit more restrictive, which is called a vector space. Okay, so a vector space is going to build on the notion of a group. So in this case now, we're going to have a vector space, capital V. It is another set over there, but now it has two numbers, or sorry, two operators, the inner operator and the outer operator. Okay. So firstly, we want the set V with the inner operator itself to form an abelian group. Okay, so it must satisfy all 5 of these properties. Firstly, for it to be a vector space, must satisfy all 5 of those properties. Okay, and then it must satisfy 2, 3, and 4 more. So we have the distributive property. Firstly, if I take a real number lambda and I have 2 elements of my set V, then either I can add those 2 elements together and then do the multiplication as in on the left, or I can do the multiplication first and then add them together afterwards. Okay. There's also the other way around, which is if I have 2 real numbers that I'm multiplying with, I can either do the sum of the multipliers, then actually multiply by the vector, or I can do the multiplication of the vector individually and then add at the end. Okay. Lastly, it now needs associativity with respect to the outer operator as well. So we know that it has associativity with respect to the inner operator because I told you it's an abelian group. Or from point 1, we know it's an abelian group. So now we need to just show associativity of the outer operator. And that is to say that if I take 2 real numbers and some element of my set V, which is going to be a vector space eventually, then I can either do the multiplication in sequence, or I can just multiply the multipliers themselves and then do it all at the end. Okay. And lastly, we know that it needs to have a neutral element with respect to the outer operator as well. Okay. The important thing to note is the difference between the two sets, or the way the inner operator and the outer operator are working on the set itself. So the inner operator is going to take two elements from the set. Okay, so we have that cross product there and V on either side. So any two vectors must now be well defined for this inner operator. And then lastly, the outer operator will take a value from the scalar real values and then multiply it by the vector. Okay, and that's why it's called the inner and the outer operator. It's the inner operator because it only takes elements from inside the set, and it's the outer operator because it uses a different set, the real numbers. Okay, that's kind of how you remember that naming convention. Okay, so let's have some examples. My apologies about this thing. I will try to clean that up at some point. So let's say we have a set V over here, right, and it is the set of n-dimensional real numbers. Okay, we don't yet know that it's a vector space, but it is a set containing these entities of n real numbers. Okay, with vector addition and multiplication by scalars, this is the most commonly encountered vector space. It's the one you guys will probably have in mind while you go through with this. But there are more general versions. So for example, if you take the set of m by n matrices, that also forms a vector space where the inner operation is element-wise addition, okay, and then multiplication is by the scalar real itself, right? Okay, so here we know that whenever I take two elements of the n by n matrices, m by n matrices, and I do element-wise addition, I will just get back to another m by n matrix, right, with real values and its entities. Same for element-wise multiplication. I'm just going to get back to another real value on all of these elements, but the matrix itself will still be m by n, and so we still have closure, and we still have associativity and all those other properties that you can prove. Okay? And that's the end of that definition. All right? So you guys all think you'll be able to do some proofs on this if asked? If I don't give you like some terribly weird set? Cool. The best strategy to do is to try and always look for a contradiction early on. Okay. Give me 2 minutes to switch slides, we can carry on. Friends online, are we still happy? Cool. All right. So we've just defined this vector space. Let V be, again, the set of n-dimensional numbers with these two inner and outer operators on them. Okay. Then U is a vector space of a vector subspace of V. If U is a vector space in its own right, if U is a vector space with the vector space operator is restricted to being the smaller set that is now within V, right? So it needs to be well defined within its own. Needs to be well defined within its own space that sits within the larger ambient space of V. So we're going to have the space V. This is the set of two-dimensional vectors. Let's do that. Then you can have another vector subspace, which is just the one-dimensional line along it, or something like that. So then U will be elements of the reals, for example. There are other ways to go about this. We can try and restrict the region of it, for example. But in general, the easiest way to do this is to look at a reduced dimensionality of it. Okay, but the whole point is that it's a subspace just because its range is now in the space of U rather than the original larger V set. Okay, and we will use the notation of, you can't really see it there, again, you remove all the little, or move around the notes, but we will use this notation here, where that is to say that it is a subset, okay? Okay, and then that, because they're vector spaces, they'll then be a subspace. Cool. So it is a subspace of V if and only if it also has its own, particularly it needs the 0 elements in there, as with all real numbers. So this kind of adds it in just because what you don't want to do now. So in the earlier definition of a vector space, you have 0 because we're just going to define it as being an element of Rn, right? And in that case, you're always then just going to have the 0 elements within that. But now what you don't want to do is restrict the space such that you've removed the ability to have a 0. Okay? If you do this, you will also contradict closure or whatever, you will contradict another property, so you don't have to memorize this point, but it's good to always just kind of check it first up and say, is the 0 element still in there? Because that they'll start to contradict all the other properties, so it's an easy thing to remember. Okay, and then lastly, you just then have to show that it still holds closure with the outer operator and the inner operator itself. Okay? If you want to prove something as a subspace, those are the only 2 steps you need. You know that all the other properties will still hold. But you just can't remove the ability to have the 0 element. You can't break the fact that now you might not have closure in terms of one of your operators. Okay? For example, if V was the R2 set, and I said that my subspace U was now R2, but only up to 100 in both dimensions. Okay? I can obviously scale that by times 1,000. And now I have an element from U that was within the 100 by 100 block, but now scaled it up, so now it's outside of that set. So I no longer have closure with respect to my inner operator. Okay? Sorry, my outer operator. And so on. Just need to make sure that you're not overly restricting your set such that these vector operations won't hold. So let's, I've preempted the first one, but does anyone want to tell me why, whether or not B is a vector subspace?
There's no 0.
Mm-hmm. So it's not a vector subspace because there's no 0 element. How about C? No? Any ideas? So let's go through it. Does it have a 0 element? Is it closed with respect to, I know we're eyeballing it here, so it's not super precise. Is it closed with respect to the inner operation? Looks like it. So what happens if I have that element there and I add that element there to it? Okay, so I'm going to go up there. I'm going to take this green vector from here and add that to it down there. So we end up there. Is that closure? There we go. And then how about with the outer operator with scalar multiplication? Does that look closed? How come? So if I take this element here and I multiply it, where does it go? That looks terrible, my bad. To use black. Okay, so if I have that vector there and I multiply it by any real value, do you think it'll still stay in the shaded region? No, I think it kind of will, because it's always going to stretch in that line, right? You can kind of see that we have this. The worst case scenario is if I take this vector here, right on the edge. If I multiply it by anything, it can still go longer. It's still then within the cone, or it can then come slightly shorter, still within the cone. It's just down there or something. Okay, so in this case, you would still have closure with respect to the outer operator. The only thing that breaks is the inner operator with the addition. Okay, how about D? Okay, so is it a vector subspace? Guys online, what are you thinking? Is D a vector subspace of R2? Chapiso, are you there? Is this a vector subspace of R2? So it does have the origin element. Okay, so D does contain 0, so you know it satisfies the first property. How about you guys in the room? Is this, what about the other two properties of closure?
I think it is a subspace.
Subspace? All right, do you guys want to raise your hands if you think it's a subspace? Okay, so let's walk through it. If I take any two elements of V, and V is quite literally just that. If I add them together, do I get back to something that is in V? Yes. There we go. 0, 0 gives me 0. How about if I scale this by some real value lambda, do I get back to 0? Yes. There we go. So it is a vector subspace. Yeah. Okay. Yeah. B and okay. So the reason B is not a vector subspace of R2 is because it doesn't contain the 0 element. Okay. If it did, like if this was shifted down here, it would be a vector subspace. That would be correct. But it's missing 0. Okay. Then if I take C here, it contains 0. We can see that it covers there. So you have the first property. If let's go with the outer operator first, so scalar multiplication of a vector. If I have any vector that's starting in the shaded region and I multiply it by a scalar, does it stay in this kind of big cone shaded region? It does, yes? All right. And then lastly, if I take two vectors in the shaded region, for any two vectors in the shaded region, will it stay in that region if I add them together? And that's the thing, it takes one counterexample. We just saw that with the 0 in my earlier example, right? I didn't think about it, but it turns out that there was this one element that made what I was saying not true. Okay, same thing here. I could take, let's say, that vector and that vector, and I add them together, and I will get maybe something sitting over, let's go black, something sitting over there like that. So there are two vectors that I can add together that will be in the space, but is it true for any two choices? And that's the main problem of this. It has to be generally true. And so I then just drew a counterexample earlier saying that if I take that vector and that vector and I add them together, I'm going to get something there. Cool. Alrighty. We good? Cool. So an interesting example is that the solution set of a homogeneous system of linear equations like we were considering last week. So it's called homogeneous system of linear equations when it equals 0 on the right-hand side. So this is where we were trying to find what was called the null space of A. So what is the set of X such that when I multiply it by A, I get zeros? Okay. So when I'm solving for the null space, I'm solving a homogeneous system of linear equations. Okay. So the solution set of that kind of system of equations with n unknowns is a subspace of Rn. Okay. Recall that you just need to verify that the subspace has zeros and that it has the 0 elements and that there is closure. So in this case, will the solution set of x's that equal to 0, will that always give me, will the 0 element always be an element of that set? For any a, we can prove this generally. So regardless of what a there is, if I multiply a by the 0 vector, do I get 0 on the right hand side? You do, right? Okay, so property 1 holds. Property 2, if I take any two x values and I add them together, will they still give me a 0 on the right hand side if I told you up front that they already gave me 0 independently? So what I'm trying to prove here is say let x, y be an element of the null space of A, and I'm just going to denote null space by capital N in this case. Okay, so what do I know? I know that if I go A times x, I get 0, and I know that if I go A times y, I get 0. But what happens if I add them together? Okay, so let's prove this. I'm going to make myself some room. Okay, so if I take x plus y, multiply it by a, we know that it satisfies distributivity. Okay, so a times x plus a times y gives me 0 plus 0. Okay, so the inner operator holds. How about the outer operator? Anyone want to talk me through how we're going to prove this? Okay, so x is an element of the null space of A. What do you want me to do next?
Anything multiplied by 0 is just 0.
Okay, so lambda is the element of the reals. So you told me you want me to multiply it by a constant, so x times lambda. What do I do with a to prove this fact?
So, I mean, we know that ax is equal to 0, right?
Yes.
And if we multiply both sides by lambda, we still end up.
Multiply both sides by lambda, but that's not exactly what we're. So that's I agree with you. You're correct, but I'm trying to kind of force out the formality that you need to structure your proofs in. Because what are we saying? We're saying I'm going to take any element of that satisfies this, and it's true, and I'm going to multiply it by lambda. So what I don't want to do is now come along and multiply both sides by lambda and say lambda, lambda, right? That's true. I agree with you, that's true, but that's kind of true by definition because I've just teed that up. I've already told you this, right? What we really want to do is come through and say this fact. And I know it's going to seem frustrating when I show you what I'm talking about, but okay. Now we want to say what happens here. And this isn't true by default. I didn't start with the equals there, okay? You then need to use the fact that we know we can pull the multiplier out in matrix multiplication, okay? Lambda ax. Now you can use that property to say lambda 0, which is equal to 0. Okay, so you want to try and always step through it. Essentially what we just did in words, where we said, well, let x be, let me change color, let x be an element of my null space. Let lambda be a scalar real value. Let's start with what we know, which is a times x is equal to 0. Yeah, that's all I did. Go for it. A times x is equal to 0, right? We know that because I've told you that x is an element of the solution space. I know it's in the null space. And then lastly, what happens if I just multiply it up front, and then you just want to show a little bit of algebra to demonstrate your points. Cool. Nicely done. Thank you. Cool. All right, and then the intersection of arbitrary many subspaces is a subspace itself. And then I'll leave that for you guys to show. It's a little bit more in detail and you have to think it through. But the same thing holds because you know that individually they all have to have a 0. Okay, so when you intersect them, you know the 0 is still there. Okay, and so on. You can then go through all those properties and say, via similar reasoning, we know that individually all the subsets held the inner and outer property. And so when I apply those two things to the individual subspaces, they will actually always stay within their subspaces. And so the union will also have the property we desire. Okay. Are we all good? I know it's been very, very abstract, and we're coming to the part of this lecture that I think is very important and most important that I'm trying to maybe rush towards. But are we all following? Okay. Let's see how we're doing. Okay. Let's take you want to take a 15-minute break quickly, and then we'll carry on with linear independence. Good. Guys online, are we happy? Thank you for your response earlier as well, Tapiso. I didn't say that. Alrighty, let's get started again. Okay, so the next definition we're going to have to come to is linear independence. We all good? Cool. So linear independence, if we consider a vector space V and a finite number of vectors within it, then all other vectors V that we can construct from a linear combination of our original set, well then they're saying that's a linear combination of the original set. And what we really care about is whether or not we can construct a zero from that combination of that set. Okay, if we can, if any scalar values there apply to each of those vectors from the vector space can give me a zero in a non-trivial way. The trivial way is when we just set all scalars to zero itself. Then those vectors are linearly dependent. They are not linearly independent. All right. Okay. And let's clean this up. Okay. If there is only the trivial solution to construct a zero out of that finite set of vectors from B, then that set is linearly independent. Okay, I think that's an old definition. But one of the main intuitions to draw from a set of linearly dependent vectors is that from the vectors you can construct at least one of the other ones in that set. So for example, I can take any of my other xi's, I'm sorry, the little note is over it, but if I take any of my other xi's, excluding the jth x, can I find a combination of lambdas such that I can reconstruct xj? All right. If that's true, then it's linearly dependent set. Okay. So to check whether or not a set of vectors are linearly independent or dependent, we can kind of just follow a simple process. It's actually the same one as we ran through last week for solving systems of linear equations. Essentially, the way to find a null space of a matrix is to try and find the dimensions of the linearly dependent columns of that matrix. Okay, so it's the same process. But to begin with, you can always just check if 0 is an element of the set of vectors we're considering, then you know it's going to be linearly dependent because any other vector, xi plus 0, gets back to xi, right? You can always just add it back together to itself. If the elements of S are not unique, then S is also linearly dependent. So if two columns of a matrix are exactly the same, okay, and these are two separate columns, okay, then obviously one is just one times the other. They're not linearly independent. Okay, and a more general complete test is that what you're going to do, you're going to take all of your vectors in the set S, you're going to construct a matrix A by putting all those vectors as columns within A. You'll get your matrix into reduced row echelon form. So again, we now want pivots along the diagonal of our matrix. So the first time you get a non-zero value in a column, then for that value, all elements to the left must be 0. Okay, so you get that kind of staircase structure where we always have zeros over there. And it's reduced row echelon form, so we know that we kind of remove these zeros above it as well. And you may have other things on the side there, X, Y, Z. Okay, that's reduced row echelon form. If you get your matrix into reduced row echelon form, then all columns with a pivot are going to be linearly independent, and then all columns without a pivot are your linearly dependent columns of that matrix. Okay, if a set is linearly independent, then you know that every single column will contain a pivot element. You will get that kind of staircase going perfectly along the diagonal elements and zeros everywhere else. Okay. A kind of intuitive concept here. If I'm embedded in R4, okay, so I have 4-dimensional vectors. So let's go X, Y, Z, and W. Okay. If I have 5 of those vectors, is it possible for that set to be linearly independent? If I have 5 vectors embedded in R4, okay, so there are all these vectors of this form here with 4 values each, right? I have 5 of them. So I'm going to end up getting a matrix that is X is an element of R4 4 by 5. So it has more columns than it has rows. Can I get that into reduced row echelon form such that every column has a pivot? Or will I end up having even just an identity block over here and then some values off the end? Call them A, B, C, D. A, B, C, D. At least. Okay, think back to last week where we were talking about having, what does it mean when we have more rows than columns? Sorry, more columns than rows. It means we'll always have a null space, right? It means there's always a way that we can take our matrix A times by X and get a 0 out. But if we can do that, then it means that we can always construct this 0 value such that we have a linear, we can do this process here. We can always construct a 0 from the other columns such that we then are linearly dependent, right? So we're tying these concepts back to trying to tie these concepts back together. So if I have more columns than I have rows, I will always have a linearly dependent set. And that at the end of the day, and what I'm building up to is just the idea of a basis here. At the end of the day, it makes sense, right? If I have 4 vectors, let's just work in R2 maybe, okay? So if I'm in this 2D space and I have 3 vectors, one there, one there, one there. Is there a way that I can construct the red vector out of the 2 green ones? We know that's always going to be true, right? We're in 2D space. I have 2 vectors that are not themselves pointing in the same direction. So I'm always going to be able to add some combination of, let's change color. I'm always going to be able to add some combination of the blue and the green vector together to make the red one, for example. I have too many arrows sitting in a 2D space to have them be independent from each other. That's the only thing that we're talking about here, okay? That's the only reason why having more columns than rows makes it linearly dependent, okay? So here's an example. So if we have this matrix A, and that's what we get to by the end of the reduced row echelon form problem, we can see that we have that vector and that vector. We now have 2 columns without pivots in it, right? I'm pretty sure this one could actually become a pivot. We should check that. But at the very least, I can always write that column as a linear function of the first one, okay? It's literally just 2 times that first column. 2 times x1 equals x2. Okay, so that we know that they're not linearly independent of each other. And here's an example that they give from the textbook and the slides that you can go check. But yeah, just put them into this matrix here. 1, 2, 0, 1, 1, minus 1, 1, 4, 2. And get into reduced row echelon form if you can. And whichever columns have a pivot, those are you can call them your basis if you want to. Those are your linearly independent columns. And then all the columns that don't have a pivot will be the linearly dependent ones. Okay. So moving towards ideas around transformation and bases and stuff like that, we can just look at this one example. So consider the following slightly more complex setup. Let's have k linearly independent vectors b1 through bk from a vector space. And we're going to construct m other vectors from this set of b vectors, okay? So we have m x values and k b vectors, okay? And so what you might ask is, what is the relationship between the linear independence of the x's and all of the lambdas? Okay, so I know we've told you that the b vectors are linearly independent. So the only thing now to ask is, well, how does the linear independence interact with the weightings we place on these different b vectors? Okay. And so as kind of I was making the point earlier, what we do when we want to prove anything or trying to figure it out, we're just going to write down what we know. Okay. So we're just going to firstly say, well, I'm going to pack my b vectors into a matrix capital B. So every vector becomes a column of that set. And we know that we can rewrite each x as a linear combination of those b's. All right. So that's definition 1. We gave that to you in the problem. All right. And what we're going to say now is that these lambdas, lambda j is just the set of coefficients that we applied to each of the b vectors to get xj. All right. The term that we're going to come to is that these lambdas are a coordinate, right? And the b's, as you can imagine, are the bases. And so now we can test if the x's are linearly independent by checking whether or not we can solve this equation, right? And again, that's the definition of linear independence. So if we say, are they linearly independent, you're going to start with what you know, all right? I am checking this fact over here, right? And we need to make sure that there is a non-trivial solution if we want to see that they are linearly dependent, right? If the only way to get this to hold is to have these phi values be only 0, then we know that they're linearly independent. Okay, please note that here we have lambdas on the b's. Those are the coefficients multiplying by the b's. And then these phi's are like your actual, it's kind of what was being used as lambda earlier there, right? Not there. Kind of what was being used over here with these lambdas to say, can you engineer a 0? We just use the lambdas. They're kind of changing notation around on us a bit. So keep an eye out. But we're now using phi as the variable to check linear independence. Okay, so what do we know about xj? Well, we've already told you it can be written as a linear combination of your b's. So we're just going to drop that in. All right. Secondly, we know that there are these two properties of matrix multiplication. The first being that you can change the ordering of the multiplication by a scalar. All right. It does commute with scalar multiplication. So you can swap the phi's and the b around if you want to. And then secondly, we know that you can have the distributive property of matrix multiplication. So here what I'm going to do is I'm going to pull it outside of the sum. Okay. And that's just the big way of writing that. Like that is the distributive property. What I'm doing here for two variables is what I'm doing here for all j of them. Okay. So inside of that operation, we're using both of the properties of distribution and commutativity with the scalar. And what we're going to end up with is now b is outside of the sum. And all we're saying is, well, is there a set of phi j's such that phi j times lambda j is now equal to 0? Okay, and so this means that the x's are linearly independent if and only if the columns of the vectors, the lambdas, are linearly independent, right? Because if this gives us 0 through a non-trivial solution, that means that this x gave us 0 through a non-trivial solution with the phi's. You see there? So all we've done is we've taken what was originally asking us for the linear independence of x, and we've rewritten it in a way that it's now in terms of the linear independence of the lambdas. Okay? And so that is then true. If these are linearly independent, there is no set of phi's such that we get a 0 unless we set the phi's themselves to 0, which is true then of everything on the left-hand side. Okay. So what does that mean if we're trying to take a slightly broader perspective? If I have some vectors x written relative to some basis b, then if my coordinates are linearly independent, my x vectors will be linearly independent. Okay, the vectors I construct from that basis will be linearly independent. If I'm given a basis and I can gather a bunch of coordinates in that space that are linearly dependent, then my vectors themselves will be linearly dependent. Okay? It's all just this idea of taking, again, we're going to come to the term, but coordinates multiplied by a basis gives you a new vector. And those properties of this vector depend on the coordinates relative to a basis. Okay? We're all fairly happy so far? All right. Fairly jargony start to the lecture. Well, first half of the lecture already, but we're coming to the main point soon. Okay, a little bit more definitions. So generating set and spans. So if we consider a vector space and we have a set of vectors in that space, call it set A. If every vector V can be expressed as a linear combination of just these vectors, then we call A generating set of vectors. All right? A can be used to generate all of V. Okay, that's not necessarily true. If I have a vector, let's say I'm considering R2 here, and then I just take the vector that's pointing along that direction there, so the 1, 0 vector. That is you can call that a set, that's a subset of V, all right? But it can't be used to generate anything along this direction, and so it's not a generating set. Right? Then the set of all linear combinations of vectors in A is called the span of A, right? So a different concept, if I take all of these vectors, regardless of whether or not they're generating of V, as long as I have a set of vectors A, then the vector space I can construct just from those vectors is called the span of A. All right? And if A spans the vector space V, then you can write it like that, or equivalently, it just spans its columns there. All right? It's important to note that this doesn't necessarily make A a basis. The fact that I can generate all of this big vector space V from A is not a satisfactory condition for A to be a basis, but it is one of them, all right? A basis needs to be a generating set of V, but it also needs to be minimal, in the sense that can't have, if I'm in a position where I can drop one of these X's and still generate V, then, now I'm not in a minimal generating set, so it's not a basis. Okay, so for it to be a basis, it needs to be slightly stronger. It's using as few vectors as possible to span the vector space. Okay, that said, every linearly independent generating set of V is minimal and is called a basis of V. All right, and we can do a very hand-wavy proof of this fact, right? Let's assume that I have a linearly independent generating set of V, right? Okay, so I know that I can produce every vector in V from a linear combination of these vectors. Okay, but let's say now that let's say it's not a basis. In other words, what I'm saying is that I could drop one of my vectors and I will still be able to generate that space. All right, but they were linear independent. Okay, so I know now that if I had to drop one of those vectors, there would be an element of that vector space that I couldn't reconstruct. Okay? If I could reconstruct it, then what that means is that from this set x1 and x2, call it, so we're working in R3. Okay? Let's say x1, x2, and x3 are linearly independent, and they generate R3. Okay? I'm going to say that this isn't a basis. In other words, I can drop, let's say, x3, and I can still generate all of the same space that I had. What does that mean? If I can still generate all that same space that I had, even though I no longer have access to x3, it means that I should still be able to then create x3 as some linear combination of x1 and x2. Let's just put lambda 1, x1 plus lambda 2, x2. Is everyone following that step to begin with? We good? All right. But that's a contradiction because that means that they weren't linearly independent to begin with. Okay. So that's the idea of why linear independence implies a basis, is because they would be minimal by definition. Okay. You can come to that same contradiction if not. All right. And then obviously if they're not spanning, then they're not a basis. You can't construct every vector in it. That's just an immediate contradiction. Okay. And so there are a number of ways of saying this, and I just kind of try to make that point with that hand-wavy proof by example. We can say B is a basis for V. For V, it is a minimal generating set. It is the maximally linearly independent set of vectors in V, or every vector is a linear combination of vectors from B, and every linear combination is unique. There's a whole bunch of ways of saying it, but it comes from that same idea that I just showed you now, which is this idea that if I had to drop one of my basis vectors, I would lose information. I would lose the ability to generate a portion of the space. All right. And that should take us to what I really want to talk about. Okay. Is everyone comfy so far? We're going to move a little bit out of the jargon for 5 to 10 minutes. Okay. So one of the things I think is most important about understanding, these vector spaces and stuff like that is the notion of a basis. It's the notion of being able to change bases to rewrite information. Okay. So I'm going to start off just by talking through what is a change of basis, and it's somewhat preempting the way the slides do it. What I will say is I do teach this different to the slides. Okay, so this is the first point. We're deviating from everything else, from the rest of the slides and the textbook. I like showing this kind of going forward and backwards and thinking about these things as being very kind of distinct entities. So let's say I have two bases here of R2, right? It's my old basis in blue and my new basis in red. Now, I want to be able to switch between bases, okay? I want to be able to represent my space of R2 here with in two different ways, let's say, in two different representations. Let's make that thicker. Okay, what that means is I'm going to have a forward and a backward transform that allows me to re-represent the space. The forward transform takes me from my old blue basis to my new one, and then my backward transform takes me from my new basis back towards my old one. All right, fairly, hopefully intuitive naming convention. So how do we do this? Well, the easiest way, and the way we're going to start off for now, is just to kind of eyeball it and say, well, I need to be able to construct my new basis in terms of my old basis vectors. Okay, so if I want to construct E1 tilde as a linear combination of my old basis, right? I'm going to use two copies of E1 added together, so I'm going to put a 2 there. I'm going to put one copy of E2, so I'm going to put a 1 there. Okay, and if I add all of those things together, I get 1, 2, 1, and I get to my vector E1 tilde. All right. I'm going to repeat this process for both of the new basis vectors. And so if I want to construct E2 as a linear combination of E1 and E2, you can maybe say it's negative half E1 and a quarter of E2. I kind of like eyeballed it while I was making the example. Okay. If I then take those vectors and I take the elements of E1 and I put them along the first column. And I take these coefficients of E2, put along the second column. I get what is called the forward transform F. Okay? It is the transform that takes my old bases and makes them look like my new ones. Okay? You can do the exact same thing with the backwards transform. What you're going to do is you're going to look at how to reconstruct E1 from the bases E1 tilde and E2 tilde. Okay? And then you take, again, 1/4 and -1, you stick it along the column there. Same for half and 2 being in the second column. So now you have your forward and your backward transforms. Okay, you can write them slightly nicer in terms of matrix multiplication. And what is important is your forward transform must always come on the right-hand side of your basis vectors. Okay, but we know that now when we do the matrix multiplication, you're going to just almost act like this is the dot product. Okay, and so you're going to end up with what is essentially a linear combination of those EK bases, right? We're happy? This is just rewriting out essentially what I did up here. Yes.
When you're constructing a new one, how did you choose the 2 and 1? So you just decided that you want to do 2.
Wait, this 2 and this 1?
Yes.
So I was looking how to construct this vector over there as a linear combination of the blue ones. So, I mean, in this case, we're not solving for anything. We're just going to eyeball it. We're going to say, well, E1 tilde is 2. You guys are right there. You're going to use two copies of E1, stick it together. That gets you 1 hop, 2 hops there. And you're going to use 1 copy of E2, which will take you up to there. That's all I was doing. My point is that for now, all we need to know is that the forward transform is what makes a linear combination of your old basis vectors such that you get one of your new ones.
But if I say 3E1, will it be appropriate?
Yeah, well, because then you would get a different basis vector, right? So if I said 3E1, that would go 1, 2, 3. You'd be out here. And then you go 1 up. You get to there. That's not the same as E1 tilde. So these values of F that I'm picking are restricted by the fact that they need to make the blue and the red basis vectors equal. Like that's the whole point. We good? That's fine. So let's work through it. What's confusing you then about that?
So when we are choosing the values, what if maybe I say 3E1 plus 2E2?
Yeah, then you wouldn't get a vector that adds up to that. You would get a different vector, which would be, just a different basis, which will be coming out to there. You can call that E star 1. You'll be dealing with a different basis. So the whole point of what we're trying to do here is figure out bases that help us solve problems. What we were doing last week when we were solving those systems of linear equations, right? We started with the perspective of my factory that had two products that were being made out of, wood and steel or something like that, right? And we said that column 1 was the fact that my company could just sell the wood, and column 2 was the fact that I could just sell the steel, and column 3 was the fact that I could make in fact, no, let's just leave the first column. So column 1 was the fact that I could make a chair out of wood and steel, all right? And it was 4 wood, 2 steel. And then I could make a table in my second column, which was 8 wood and 8 steel, or 16 steel, or whatever you want to use, right? And that was representing these columns, representing these products in terms of wood and steel. And then we wanted to change the way we were representing the problem until we got 1s along the column and 0s everywhere else. And what that corresponded to was changing my basis from wood and steel to changing to a basis of desks and chairs. Okay, so this basis that I've given you here, it looks arbitrary because it's just, red and blue bases. We're just using an example. But these will in most cases be meaningful. They're the bases that get you into row echelon forms that you can read off your solution, for example. And that's why you're often going to have to solve for these in a test, there's examples here, tutorials, where you will just solve for what makes that matrix work, right? It'll be a lot more maybe tangible in that respect. But all we're saying is I want to be able to take my blue vectors, multiply them by some matrix, and get red on the right, on the left. Yes.
So we're given the red vector.
Yeah, you'll be told which bases you want to map into if you need to figure out the transformation, right? You need to be given at least 2 pieces of this at any given time to solve.
I think that's why I don't want to finish. But given that red, it's not something we can just solve.
I mean, you would, in theory, be solving it though, right? Because you would say, what, new basis, so let's just go, B tilde is equal to B times F, and if you wanted to solve for F, you would then have to invert it, so you'd get B inverse B tilde is equal to F, and then now that gives you this matrix, right? But I've told you what B and B tilde are in that case, in the same way that I just told you what the blue and the red vectors were. You good? Okay, if not, please do kind of ask again, maybe in the break. Because this is important to how things will proceed. Okay, and then the last thing just to note is that the forward and the backward transforms are inverse of each other. So if you take the product of the forward and the backward transform, you get to the identity matrix. You can solve the backward transform if you want. You probably will never do this, but if you wanted, you could first solve for the forward transform and then invert it, and then you would get back to you would get the backwards transform. Okay. The whole point of them both being bases is that inverse will never be singular, right? Because if it's singular, I cannot reverse it. But if I couldn't reverse it, it means that the new basis, the new set of vectors, would have lost some information. I wouldn't be able to represent the same space with it. Okay, so by the fact that I've told you that both B and B tilde are a generating minimal set of vectors, you know that you can map arbitrarily between them and you'll always be able to reverse that. Okay. The important thing to note then is that the whole reason we're defining bases is so that we can write other vectors in terms of it. Yes, I'm going to switch to black. Okay, so in this case, we're talking about that V over there, the green vector. sitting in some arbitrary space, right? Sitting in this 2D space. I can represent the green vector in terms of the red basis or the blue basis. All right, here it is. This is how you do it. That's for in terms of the first basis. And so what I will often do is just write this as a coordinate vector, okay? And then I'll just write EI over there, right? So that's in terms of the blue basis over there. The alternative is I can also write it in terms of the red basis. You get different coordinates though. And that's what matters. The way that I am thinking about this vector V has changed its coordinates because I'm writing it in a different coordinate system. I'm writing it relative to two different bases, okay? But, so if you want, you can write it, the vector like that, which is more of the matrix multiplication form. And again, your basis is on the left, all right? And so remember last week and earlier today, we were talking about multiplying columns of a matrix. This forms a matrix, right? Those are two vectors. And then this is a vector in its own right. And so when I do this matrix multiplication, what I'm doing is essentially taking this linear combination of E1 and E2, right? Because at this point, this is a dot product. We know that it's just going to end up being E1 times by 1. So E1 times by 1 there. Plus E2 times by 1.5 there. So 1.5 E2 there. And that gives me V. All right? Simple matrix multiplication, simple dot product representation of matrix multiplication. But that's kind of why, like I said last week, I like representing and thinking of matrices as vectors with vectors along its rows. Okay? So I've just written this as a row vector where E1 and E2 are themselves column vectors. And now you get back to this idea of it being a linear combination. Any green vector is a linear combination of your bases. Okay, I can do this same representation for V. What for the red bases? What matters though is I just showed you earlier that I can map arbitrarily between them, right? I can change my basis from blue to red. And that is exactly what I'm going to do now. Okay, so if I change my basis, this representation of V here from blue to red, I'm going to represent blue in terms of red. Okay, and that's that matrix we found earlier. And then when I FOIL everything out and I solve for the matrix multiplication there, what I end up with is 1, 2 on the right-hand side, and now E1, 2 tilde on the left, my red basis on the left. And you can check, it's exactly the same. All right, the same as what I defined earlier. Same thing here, I can take my red basis over there, replace it with the blue vectors, just applying the change of basis formula from the left-hand side, do this multiplication there, and I get back out to my original blue basis vector there. Okay. So ideally, that's what we want, but what you will have noticed, all right, and this is the subtle point here, what you will have noticed is the forward and the backward transform are opposites if we're talking in terms of bases and coordinates, right? Over here on the left, when I was doing the basis transforms, to go from my old basis to my new basis, I multiplied by the orange forward transform, right? On the right-hand side, when I was going from my old basis over here to my new basis over there, I multiplied by purple, which is the backward transform. Okay? And so if we're talking about changing bases, okay, and I say, what is my, here is, here is a forward transformation, and here is my old blue basis vectors. What is my new basis? You'll do that matrix multiplication. You'll go blue times forward. If I ask you, what is the coordinates of this green vector in terms of my new basis? Given the old basis, given the fact that this is how the coordinates in that old basis, you will use the backward transform to update the coordinates. Okay? So coordinates and bases act opposite. That's the main point to hold in mind here. And so the whole idea of this, and you can see this happening in a really simple case here of me just stretching my bases, right? So again, I have blue basis, red basis. If I am stretching my basis vectors from blue to red, So now my basis is getting twice as long. My coordinate of the green vector in terms of those bases gets half as long. Okay, I used half of the red basis now to represent the same vector. And the same idea holds in one dimensions, right? If I drew a line on the ground going off into the distance and I told you that line was 1 kilometer long, we could change our basis, we could change our unit of measurement to meters, right? So I am taking a kilometer, making it meters, so my unit of measurement is becoming 1,000 times shorter, and so my coefficient must become 1,000 times longer. 1 kilometer becomes 1,000 meters. And that is all that's happening. It's just now happening in linear algebra. It's the same exact idea as one dimensions, okay? And that's a really important point of keeping in mind whether or not you're speaking in terms of coordinates or basis vectors, because they act opposite, because they must always be what the word is conserved. They must always be operating the same way to keep all your representations of V the same. Okay? That is going to come really important when we start getting to, number one, transforms, but also ideas around changing bases like your singular value decomposition in about a month. Is that vaguely clear to everyone? Again, it's this inverse thing is a bit subtle, but everything else here should be, apparent.
So I get how you would find the minimum basis in one dimension. But for 2 dimensions, how would you then, let's say in this case you have 2 bases, right? How would you choose the most minimum one if both of them are bases basically have 2? Do you look at their projection into X?
They both have to be minimal for it to be a basis, right?
Oh, yes, exactly. In this case, we're calling them both bases, but they have 2. So that means one of them is not a basis in that case.
Okay, so keep track of the fact that you're not going to be using them simultaneously. So you're correct that if what I did is then I said, let's work with this set, which is E1, E2, E1 tilde, and E2 tilde. This is definitely not a basis. You're correct. We have 2, I've just shown you that we can always draw that as a linear combination, that as a linear combination of your first 2, right? But you're using them independently. And again, the idea is taking it back to that example from last week with your desks and chairs. The idea is that I shifted from a basis in terms of wood and steel to a basis in terms of desks and in terms of desks and chairs, right? But the good news is that I wanted to solve an answer. I wanted to answer something about how many desks and chairs do I produce. So that was an easier basis to read that answer off in, right? And so that's exactly what just happened in that case, right? We knew that we were going, so we started with, we started with AX is equal to some B, right? And AX was in terms, and B was in terms of desks and chair, or of wood and steel, which meant that I had, again, 4 and 12, and I always have to make sure these examples on the spot aren't linearly dependent. 8 and 2. Okay? Times by X must be equal to B. Okay? And again, that was when I started the problem. I told you that to produce a chair, that's how much wood row 1 and steel row 2 I needed. Okay? To produce a table, that's how much I needed. And then I took it into row echelon form. Okay? And I got something that looked like this. 1, 0, 0, 1. Okay? We got X equal to B, and now B has changed so that it's conserved, right? Whatever I did on the left, I did on the right to B. This basis now is an identity basis. It's orthogonal. Okay? What it means is that this now looks like Euclidean space. And so I have that vector pointing up there and that vector pointing up there, where over here, this basis I was working in there was looking all, squiggly. It was like pointing off over there, and another one was maybe, I should make one of these negative just for argument. Another one was pointing off there. That's a hard basis to read solutions off of. And so I just changed basis to 1s and 0s because there was like meaning behind the numbers I used. My basis that I changed to has meanings. It's gone from a basis of desks and chairs to a basis of, it's gone from a basis of wood and steel to a basis of desks and chairs. And so now I can read off the coordinate of X, which makes that true. Sorry, that probably was way more than it needed to answer your question, but all right. I hope this is at least making a little bit of sense, is still being a little bit clear. And so if you take one thing from this example, again, it's the fact that basis coordinates are opposites. You can always just map back to the one-dimensional case of line on the ground, 1 kilometer or 1,000 meters, same thing. And we're just doing something a little bit more complicated here. But the operation, the idea behind it, same exact thing. Cool. And we can get back to the slides. Is everyone feeling all right with that? Cool. Let's push through for a couple more minutes and then we'll take another break and kind of let things set in. So generating sets and basis properties. Every vector possesses a basis B. The basis is not necessarily unique. So to your question, there are multiple that might work. All of these are bases of R3, right? If you try to take this and get into reduced row echelon form, you would realize that ultimately you would get to something like that. Same for this bit over there. You can get into a reduced row echelon form, which has pivots along every column. Okay. In the case of finite dimensional vector spaces, the dimension of V, is, the dim V, this operator kind of representation, is the dimension of V, which is the number of basis vectors used to represent V, right? If U is a subspace of V, then the dimension of U must at least be as big as V. It cannot be more than V, so it may be less, right? If they are equal, then this only occurs when they are actually the same vector space, right? So when you have vector subspaces, you will almost always be dropping. You will always be dropping a dimension, except in the trivial case where they are actually the same vector space, all right? And that goes back to that proof I showed you earlier with that x1, x2, x3. If I dropped x3, I must be losing the ability to represent space if that was a basis to begin with. If I haven't, then it means I could have constructed x3 from x1 and 2, which means that it wasn't a basis. It wasn't minimal. All right. And so now I've dropped x3. And so I've lost the ability to represent one direction of information. And so now my dimension is smaller. Okay. Okay, so basis of a subspace can be found by doing the following process. So we're going to take a basis of the subspace U, can be found by the following steps. Write the spanning vectors as columns of matrix A, determine the row echelon form, and then the spanning vectors associated with pivot columns are the basis of U. All right. A lot of times we talk about a subspace of Rn, so that's kind of like the bigger ambient space that it's in. All right. So I have some kind of like cube box on the table here. I have a subspace of that box. Okay. If I took my phone over here, imagine it's projecting out infinitely and it's everywhere, but it's this flat 2D object sitting in a 3D room. And so I've lost a dimension. All right. There is this direction there that I would need another vector to represent. I can't see anything off the plane defined by my phone, but it's still sitting within 3D space, right? This point here at the bottom left of my phone, it's still some height off the ground, some distance away from that wall, and some distance away from that wall. So it's still a vector in R3, but the subspace itself, the vectors I can represent, are restricted to lying on that plane, right? So keep in mind that there is a difference between having a plane that is R2 and having a two-dimensional subspace in R3. Those are different things. And again, it's as we start building up definitions and getting a little bit more and more kind of content within the course, it gets really subtle to remember that. So there is a difference between saying that there is a vector space in R3, a vector subspace in R3, and it then actually being R2, for example. Okay, we good? And so, for example, you guys can try this at home. You can determine whether or not, or which of these vectors are a basis. So my earlier question, do you think that this entire, all 5 of these vectors are needed to form a basis? If I wrote, let me be more formal about that. Let's say if I wrote A, B, C, D, E, is this a basis of R4? Why not?
you'll have one column that has a pivot, so there'll be infinitely many solutions.
That doesn't have a pivot.
Yeah.
There we go. Okay. So I'm trying to represent 4D space with 5 vectors.
Speech to the young.
Cool. All right, and then another definition is the rank of a matrix, and rank is important, especially as we go further into single value decomposition. So let A be an n by n matrix, then the rank of A, denoted as this RK thing, so it is different to the dimension, is a number of linearly independent columns of A. Sorry, it is written differently to the dimension. So it's also important to note that if you transpose A, the rank will stay the same. Right, so the rank of a matrix is also the same number of linearly independent rows of A. And we'll prove that in a couple, probably next week. We'll get to what's called the rank nullity theorem, and it kind of combines all of those intuitions. Okay, so yeah.
Question. If A was invertible, will the rank still be the same? Like if the rank of the inverse of A will still be the same as the rank of A?
Yes. Sorry, let me think about that. So yeah, because if you drop rank, then it's not invertible. Exactly. So the fact that you can go A and A inverse means that the rank has to stay the same. If the rank of A is less than the dimension that it's embedded in, then it's actually not invertible either, right? So you can then always drop that column, but yeah, I guess if you have an n by n matrix, yes. So it needs to be squared for it to work. Okay. So the columns of A for an n by n matrix span the subset U, with the dimension of U being rank A. The rows of A span a subspace W. It's a different subspace now. Obviously, it's embedded in Rn and R. The earlier one is Rm, with the dimension of W being the rank of A. And so for all A n by n, it holds that A is invertible if and only if the rank of A is n. Okay, so to answer your question, but Yu is correct. It had to be n dimensions there. Okay. So the rank of a matrix has some useful properties. So again, A is now a m by n matrix. And for all B, which is m-dimensional vectors, it holds that the linear equation system AX equals to B can be solved only if the rank of A is the same as the rank of the augmented matrix. Okay? What does that mean? Let's consider the inverse. What would happen if I included a vector B and that made the rank larger? Sorry? So maybe trying to express in terms of bases or just notions of space. You can tell me about squeezing a box or whatever if you want. If I took a matrix A, I added a column B to it, right? And the rank increases. What would that mean? And why does that mean I can't solve the system of linear equations then?
I think so. Maybe I'm not understanding the question right, but like let's say you have a 3 by 3, right? And then you add vector B that has 4 columns. You couldn't have any combination of the fourth.
So B is itself just it's a vector, right? So it's just Rm. But carry on.
Yeah, I'm saying like because A originally is a 3 by 3.
Yeah.
If now B is 4, right? The bottom value, there won't be a linear combination of, I guess, the fourth value in A that will lead to B. Maybe I can draw this up.
So is A necessarily a square matrix? So
Yeah, A would have to be. So again, it's if you want to solve the system of linear equations here, it needs to be at the very least n needs to be greater than m.
Okay.
Right. So the kind of whole point of that is if you have these excess columns of A, you want to still have a like sub matrix that is fully invertible. Right. Yeah. Okay. So what's the answer to my question, and again, it was a tricky one, is if I add this column B to A when I'm forming my augmented matrix, right? What has happened? If my rank increased, I just added a column that I couldn't represent as a linear combination of my earlier vectors, right? By definition. So what does that mean? It means that I couldn't find any sum of the columns of A to represent B. But that's exactly what I was trying to solve, right? A of X is equal to B, right? Where A is these, A1, A2, A3, however many you want. Those are their own vectors. Multiplied by my X, that gives me that sum Xi, Ai that I was trying to solve to be equal to B. Put a different way, if I've increased the rank of B, I've added information into the system. I've added a dimension, okay? So it would be like me trying to define a plane with my flat phone screen, all right? And then trying to represent a vector where the projector is. There is no way that I could do that. How would I move along a plane defined that way and get there? That's the entire kind of like idea of this notion of rank. So if I append a new vector and the rank doesn't increase, it means that I had to have been able to create that B vector from the others to begin with. Okay, so we know that the rank shouldn't increase. We shouldn't add dimensions to the space. Okay, and then somewhat importantly, if A then defines, if we're looking at solving the homogeneous system of linear equations, the rank of the solution space to that is n minus the rank of A. Okay, and again, think back to the example I just made. All right, so my columns of A define a 2D plane in this room. I can move along this plane anywhere. I cannot move along that diagonal over there. So that is the null space. That is the space of vectors that I will always get mapped to 0. They will always get mapped back onto the plane. So the excess dimensions is n. So n is the space that we are embedded in. It's R3. A defined a 2D space in R3. And so you have that number of excess dimensions is what we cannot represent. It's what becomes the null space. Okay. So the matrix A has full rank if A is the minimum of m by n. Okay, we say it's full rank if it has, whether or not you have more or less rows or columns, if the rank is equal to the minimum of those two things. Okay, it has as much, it represents as much space as it can. None of your columns, for example, or rows in that case would be linearly dependent. Okay. Again, we'll tie this all in with the rank nullity theorem next time. I understand that this is now starting to get a little bit more unwieldy. But I think the important thing, again, that for today's lecture that we really need to hang on to, the definition of groups, obviously, but then this idea that your coordinate vectors are ways of representing space in terms of a basis. If I change a basis, the coordinate vector changes in the opposite way. For those of you who do game design or anything like that, that should be pretty obvious. Because if I take my camera and I move it to the right, it's the exact same way as the world moving to the left relative to me. That's the exact way it's coded up in terms of games. And so that's the idea. I took my camera, I moved it to the right, I changed my basis, or it's the same equivalent thing as moving the coordinate space. That's, if you're not a developer, then that doesn't matter to you. So that's the second thing we care about. And the third thing we care about today is this idea of having a vector subspace embedded in a larger space. So it could be in R3, okay? And so if we have 2D space embedded in R3, we will still have bases that have 3 coordinates, A, B, C, X, Y, and Z, right? But I only have 2 vectors that I can represent that space with, okay? So the embedding dimension, n, is the number of rows that I have, okay? The actual rank of the space that I can represent is the number of columns. All right. Those are 2 different things. We can have a 2D space embedded in R3. Okay. Let's take a break from that, and then we'll come back and just wrap up with some linear mappings. How are we all feeling? We good? So one cool example that actually came up during the chat now that I'm going to share with the rest of you is we talked about earlier how the intersection of two subspaces is itself a subspace, right? And so the example that we were just using is, let's say I'm in this 3D room. I have two subspaces, the one that's defined by the right wall, and the second subspace is the 2D plane defined by the back wall, right? Okay, so we have 2D planes defined sitting in 3D. Where do they intersect? Right at that corner there, right? To the people online, I'm pointing at the corner of the room. They intersect right at the corner of the room, right? So I had my first plane here, second plane there, they intersected there. All right? We know that both of those two planes had to contain 0 for them to be vector subspaces, call it the bottom right corner there, right? So now the intersection between them still contains 0, all right? The second property we care about, if I take any two vectors in a subspace and I add them together, does it stay on the subspace? Well, if I take any two vectors sitting along this corner here and I add them together, do they still sit on the corner? And yes, I can only move up and down. And then if I scale any vector on the corner there, it doesn't stay on the corner. Yes, it does. It just gets increasingly higher, increasingly close to the ground. Okay, so that's the main idea of why intersection of subspaces is itself a subspace. Exactly what the walls did by intersecting there, forming a line at the intersection of two planes, will happen in general dimensions. Okay, you might take two 4D cubes, intersect them and get 4D, tesseracts or whatever, intersect them and get a cube. We tend not to imagine those things because it's hard, but we can think when we do a proof, we will start by thinking like that. Okay, and then from there we move on and say, okay, can I generalize to higher dimensions? And that's when you need a bit of symbols on paper, I guess. Cool. And it goes to my earlier points last week of saying, I think maths is about finding good analogies for things, right? I like the analogy of a change of basis being a one-dimensional line on the floor, and then you're switching from meters to kilometers. That helps me conceptualize what's going on and why coordinates act opposite. You guys might find your own, set of interesting things that help you visualize what's going on. Okay, and then you just know when to pull out your tricks. We good? All right. Okay, let's speak about a linear mapping now. So for vector spaces V and W, a mapping defined by phi is called a linear mapping if the distribution property holds. Okay, so it's actually two different things within one. Firstly, I can take this phi operation inside and get the same thing. So you can see I wrote that out there. Oh, it's the second one. I wrote that out there. Okay, so given any two vectors, phi can be distributed and work on them independently, and then I can add it back together. And then secondly, if I have a scalar, I can first scale a vector and then apply phi, or I can apply phi and then scale. Okay, if those two properties hold, then that is a linear mapping, right? It's also called a vector space homomorphism. Morphism is a kind of word to mean that you transform something. Homo, as in it maps back to the same set it started from. Okay, we can represent linear transformations as matrices. Okay, when they're in finite dimensions. There are ways to get into functional analysis that generalize these concepts, but we just care about vectors in finite dimensions now. And so we can then represent any linear mapping with a matrix. Okay, there are a few kind of nice definitions to know about with these mappings. So if you consider some mapping from a vector space V to a vector space W, where V and W are arbitrary sets, then phi is called injective if for every x and y, the mapping, if I map x and I map y separately and they are equal, then it means the original vectors themselves had to be equal. Okay? It is surjective if I can reach every point of W from some mapping off of V. All right, so the mapping off of V gives me the full space W. And then lastly, it is bijective if it has both properties. And fortunately, this is kind of easy to draw. And again, you will never really have vector subspaces that are like these distinct things floating in space. It's easy to think about sets this way, but more often than not, vectors, subspaces are dropping dimensions in this ambient space, right? So that's always you're always going to be able to like move in an infinite direction along a basis vector. But it helps if you think of sets of vectors in the same way you do sets of, you know, I don't know, combinatorics kind of sets of just entities. Okay, so for injectivity, every point in X can be mapped to another point in Y. All right, someone intuitively there. Then surjective, every point in Y comes from a point in X. And then lastly, if I combine them, it's invertible. It means that I can take these 3 points here, get to 3 points there, and I can move backwards off of that. Thinking in terms of bases and mappings and that sort of thing, what does it mean? If something is invertible, it means I have not lost information. Okay? So again, if we're moving away from this idea of thinking in terms of these little combinatoric sets and thinking in terms of vectors in space and vector subspaces being removal of dimensions, then if I can map out of it, it means that whatever I represented in terms of 3D space here, it had a particular mapping to a different kind of 3D space on the right. And I could take it backwards. If I can't, it means I've lost information somewhere along the line, right? And that means that I had what was a cube, and I'm not the best artist, but I had a cube, whatever, and I mapped onto a flat plane. And I have this point here, okay? I cannot map out of that plane because how high must I put this dot? Maybe I can know, for example, that it will go to there. I can determine 2 of the coordinates maybe, but I cannot tell you anywhere how high that must go there, okay? And that's what we were talking about with that null space the other in the previous slide, right? We were saying that the mapping, it has a particular rank, and the rank is the dimension that it projects onto. So I start in 3D space. I have this A mapping that takes me into 2D space. Yeah, it might be embedded slightly differently, but actually it's only 2D space. All right. So I have a rank of 2 operating on these 3-dimensional vectors. The dimension of the null space is what's remaining. It's the space that I cannot tell you about when I try and invert it. Okay. So I had a 2D space here and a 1D space over there that I can't reconstruct. And so what do we get to? We get to the fact that my rank is the space I cannot represent. My null space is n minus the rank of A. Okay? In that case, this is the null space. It's the space of vectors on my left-hand side that when I multiplied by A, they got mapped to 0, they vanished. Okay? That's the whole point. Regardless of how I move, and this is going to become a very thick green line, no matter how much I move in that direction, it always collapses and gives me a 0 on the right-hand side. Okay? This, what I've just drawn, is the rank nullity theorem. The rank of a mapping A, okay, how much space it drops me into, and how much space I forget on the left-hand side must equal the amount of the dimensions of the ambient space that I'm in. Okay, I'm in a 3D cube. I drop you into a 2D plane. I must have lost 1 dimension of movement. All right. Cool. So a bijective mapping can be undone. There exists a mapping, I don't know, gamma, whatever that is, so that when I combine them, I can return back to the same representation. This mapping is called the inverse of capital Phi, and is normally denoted as capital Phi to the power of -1, as all inverse things are, right? Okay, so when I go capital minus Phi, combined with Phi, I should get back to the identity mapping. In other words, I don't change anything. If I did change something, then it's not an inverse, or I've lost rank. Okay, is it clear why we need square matrices from this to make sure that it's invertible? No? Yes? No one looks super convinced. Yeah.
Because if it's not square, when you try to get the inverse, if you go from an m by n, you'll get to like an n by m.
Exactly.
So it'll be the wrong way. So
you'll drop into a lower subspace. There we go. Cool. Everyone get that? Cool. It has to stay in. I have to be projecting from n into n to make sure that I'm keeping the dimension the same. It has to keep the rank, has to stay full rank. Right, we're good. All right, then if we have two vector spaces, there's a bunch of other named types of mapping. So you have an isomorphism, and that's a mapping that is both linear and bijective. You have an endomorphism, which maps from the same space to itself linearly. Okay, and then you have an automorphism, and that is linear and bijective and mapping into the same space. I'm not going to test you on these names. They're all a little bit vague to me, but yeah.
What's the difference between automorphism and identity mapping? Because from what I see, they both like they map from B to E.
Yeah. So as you can see here, the fourth point says, so we can define the identity mapping IV or identity automorphism as what goes from V, and so it's a special case of the automorphism is the identity mapping. So the identity mapping also maps from V to V, right? Okay, and it can also be linear and bijective. The point is that the identity mapping doesn't change your representation of space, whereas an automorphism might. You know, so if I like rotate my basis. Cool, good, yeah, good question. Okay. Okay, and so you have this theorem 3.59 in the textbook. So finite dimensional vector spaces V and W are isomorphic if and only if their dimensions are the same. All right? Again, if I took something in a cube and I mapped it onto a square, the dimension of the cube is 3, the square was 2, we've lost rank. It's no longer invertible. Okay, so this theorem states that there exists a linear bijective mapping between two vector subspaces of the same dimension, and then it is possible to transform from V to W without incurring any loss. And in this case, when you speak about linear algebra, incurring loss means that there is a dimension that I cannot represent anymore. Okay, I took my box and I squashed it, or so on. Okay, so if V, W, and X are vector spaces, then a linear mapping between V and W and another linear mapping between W and X, then I can compose those two mappings and I get back to something that takes me all the way from V out to X, and it's also still a linear mapping. So you can see the diagram I drew at the bottom here. Okay, I can start with a set V. I can either use the phi mapping to get to W and then use the gamma mapping to get to X, or I can compose my mappings and then just jump straight there. Okay, those will still be the same linear mappings. And that's just because, you know, matrix multiplication works that way. You can always string these matrix multiplications together, and because matrix multiplication is associative, what I can do is either I can go, let's go phi, gamma, X. Either I can do that first, or I can go phi, gamma, do that first, X. Okay, this is the second case of this, and this is the first case of this.
So it's a little bit pedantic, but I think that's a psi instead of a gamma.
Thanks. Cool. We good? Okay, so we get to the definition that I've already kind of given you, so we're going to go a little bit quickly through this now. It's coordinates. So consider a vector V and an ordered basis B1 to be n of that vector space for any x in V. So again, any x in the vector space itself, we can obtain a unique representation of x in terms of the other vectors, your basis vectors, and that's lambda 1 through lambda n. Okay, those will give you the coordinates of x with respect to the ordered basis. So earlier, x was the green vector, B1 and B2, Bn were either the red or the blue vectors. Right? And we always came to our coordinates for that. Right, and then we can say that alpha is our coordinate vector. I always prefer to kind of say what the basis is. So like I would like to do that, but you don't have to. Obviously, it's always implied. But I think that it kind of always helps differentiate a vector from the coordinate of that vector relative to a basis. A vector is a tangible thing, okay? The basis itself and the coordinate in that basis, they just need to be conserved. But those two things you can give and take. You can always, again, multiply your basis, divide your coordinate, or so on. It is, in many respects, the basis you choose is arbitrary, okay? What matters and what we're going to come to is cases where that basis is not arbitrary anymore. We saw one last week, right? It's the basis that allowed you to solve your system of linear equations and just read off your coordinate that satisfied your condition. Okay, you change basis from wood and steel to the two products you want to produce. That's one change of basis that was helpful to the problem. But again, your bases are arbitrary, and what we're looking for is ways to change and manipulate your bases such that the solution to a problem falls out. That's the whole study of this thing. Okay, of linear algebra. The most familiar coordinate system is the Cartesian coordinate system. So this is only in the case of R2, where you are spanned by the identity vectors E1 and E2 that I've drawn at the top. And so your basis, therefore, is just, you can append E1 and E2 together to form your basis. If the vector X was represented as 3 and 1 transposed, obviously, because we always want column vectors, using B, how would it be represented using the basis but swapped? Okay. Well, if I have permuted my basis vectors, I must permute my coordinates, right? That's another example of that change of basis I was telling you earlier. In that case, we were scaling things, but there is a linear transformation which will swap my bases, right? It's actually this one. That's known as a permutation and vector or mapping. And so we can just apply that. We'll swap my two columns, and then you just must also then swap your two rows. Okay, there are many valid coordinate systems. We have just gotten most accustomed to the standard Cartesian coordinate system, where the basis vectors are simply these like axis aligned bases to the ambient space. All right, it's nice dealing with zeros. That's like pretty much the only reason we really care about this representation. Okay. And then for an n-dimensional vector space V in an ordered basis of B of V, the mapping defined over here, right, is linear, where you have the same basis of Rn. And so what this is saying, in essence, this implies that we can always find a mapping from each Eij to a new basis, Bj, right? So we can always map out of our Cartesian coordinate space, or it's in high dimensions, it's typically called the canonical basis, right? So we can always start in something that is axis aligned to the R3 dimensions and then map into another basis with a linear transformation. One thing I do just want to, I think it comes up now actually. Yeah. One thing I want to mention now just about the way the textbooks represents transformations is that it kind of does it backwards. So that process I was doing earlier of taking my red vector and constructing blue out of it, or taking my blue vector, constructing red out of it, that's largely what this book tries to do. But what you'll notice is that they're operating on the B's down there, right? And that gives you a linear combination C. So in other words, this phi, in my opinion, is always the backwards transform. And the textbook doesn't do it both ways. Okay, that's why I try and do that that example earlier, so that it's clear that what you do is you're going from forward to back. So you're going from your initial bases to your new bases using the forward transform. You can take it from the new to the old using the backwards transform. The coordinates also operate in the opposite way. If you read the textbook, 2 of those 4 things are going to not show up. Okay, they will only show you how to construct for whatever reason, your old basis out of your new basis, and then they'll tell you that that's the mapping A, right? To me, that is the backwards thing. What I will get from all of these alphas will take me from my new basis representation and give me my old basis. Okay. So just be really, really careful if you're going to read the textbook for this. Just be really careful that you're keeping track of which direction that operation is going in terms of your bases. Okay. The matrix that can take you from C to B is the backwards transform in that example that I showed you. Okay. What they will call this now here is the transformation matrix. The reason they've done this is because it becomes easier than to work on the coordinate side, right? So I told you that the coordinates, when I change basis, if I'm using the backwards transform on my bases, I'm using the forward transform, I'm doing the forward mapping on my coordinates. That's why they've used this. Because what they're ultimately going to do is they're going to take this A and they're going to start speaking in coordinates. So they had to define it backwards here, so we only have these two cases. I prefer to think of being able to go backwards and forwards, and then just being really, really careful about which direction I'm going in, and being really, really careful about whether or not I'm speaking about basis or coordinates. It's up to you guys. If you like the way this does it, by all means, I will talk you through it now for a second. But I just want to be really clear that there is just subtlety to this, and it's in the notation, and it's in this ordering of the summation, and it's a little bit unwieldy sometimes. If you want to, you can just keep in mind, again, forward, backwards transform for basis and coordinates, and you have 4 different things you have to think about. Cool. All right. So considering vector space V and W with corresponding ordered bases B and C, and again, to the earlier question, we are given B and C. We are told what these bases are. Then there is a linear mapping phi, which takes us from V to W. All right. And in this case, the way that it works is we will take each basis vector Bj and represent it as a linear combination of our new basis vectors, or the basis vectors of W, right? In that sense, when we take all of those coordinates, all right, for one of those vectors, exactly as I was doing when I started that blue-red example, and I'd put them into a matrix A, right, where the first column is the coordinates of my first basis vector in terms of my new basis. Okay, so you just take that your first B, you represent as a linear combination of those C's. You take all those alphas and you make it your first column. For the second B, you do it the second column, so on. Okay, you will get the transformation matrix between the two bases. All right. And so that is according to the textbook, the transformation matrix of phi with respect to the ordered basis B of vector space V and the basis C of vector space W. Right. So the coordinates of Bj, this Bj mapping with respect to the ordered basis C of W are the jth column of A. So again, matching the J's. For the first vector, the coordinates you get go down the first column of A. Exactly the colored example we did at the start. Okay, so then consider a finite dimensional vector space V and W with the ordered basis B and C and a linear mapping between them. All right, we can get that matrix A that maps between them. As you can see now, if X is a coordinate vector of, if X hat is a coordinate vector of X with respect to B, and Y hat is the coordinate vector of Y with respect to C, then you can map between them. But keep track, right? Again, X is in the original space. Y is in the new space, okay? We're using A to go, in this case, from a vector of old to new. We know that the coordinates worked opposite. We know that old to new in coordinate space uses the backwards transform, which is what we were constructing over there, right? So please don't, read this. Don't read that slide and forget that this slide is talking about bases, all right? And this one is talking about coordinates. It gets really confusing if you do that. The only time linear algebra gets confusing is if you lose track of whether or not you're talking about a vector as in the line on the ground, or you're talking about your basis, or you're talking about your coordinates of the line on the ground. If you keep those two things separate and you figure out how to map between them, and you're really disciplined, this entire field is easy as it can be. All right, we'll stop with this technical detail this week as well. It gets more kind of like geometric next week and the week after as well. And you'll realize that there's no new concepts beyond what I've just really spoken about in terms of changing bases, keeping track of coordinates, keeping track of what's happening to your vector space, conserving vectors. Okay, so you can go through this example, but so if we consider a homomorphism and an ordered basis B of V and C of W, then for argument's sake, let's say you can write your B1 vectors in terms of C. So that corresponds to going A times C is equal to B, right? You can see the A, these alpha things are on the right-hand side multiplying C. Okay, so what would that give you? That means that I'm going from new basis to old. So this has to be my backward transform, right? Back. All right. Sorry, I'm harboring this point, but I think it's because it's the thing that matters most to me, I think. Cool. So you're going to get your backwards transform. We're going to call that A, all right? That is now, according to the textbook, the transformation with respect to B and C. Okay? That, in this case, is the representation of that matrix because we took the coordinates of B1 with respect to the new basis. Okay, so those values up front here, and we made it our columns. Okay, so that 1 becomes there, then after that it's -1 over there, then the 3 goes there, and then -1 there. All right, do the same thing for all the other rows and columns. All right, I'm going to skip that for now. This is another thing I've spoken about in terms of how do you think about what neural networks are doing, or at least linear regression is doing. But we can speak about that later on. I actually might just take that out. Okay. How are we feeling? Are we keeping track of where we're at? I keep picking this up. Are we feeling okay?
I think there was an issue on the last slide.
Okay.
The 4C4. Yeah.
Okay, so that's 1 minus 1, 3 minus 1, so that's 2, 1, 7, 2.
Especially 4C4.
All right, 3, 1, yeah, that should be 1, hey?
Yeah, well, I guess 4, 1, 2. Same.
Oh, yeah, let me just do it that way, yeah. Going badly, I guess, but good catch. Alrighty. Let's see, what slide are we on? 40 out of 51. All right, let's get to a checkpoint here. Okay, we have 5 slides to do. Let's get this done and move forward. Okay. All right, so consider 2 ordered bases of V and 2 ordered bases of W. And you currently have the transformation matrix A of the linear mapping from V to W with respect to the bases B and C. So a lot going on here. We'll draw a picture of this. So how can you find A tilde, which achieves the same transformation, but just with respect to our new bases B and C tilde? Okay, so what I've given you is 4 bases. Again, you're going to be given the bases because that's how I want you to set up the problem. Okay, now I've given you another mapping from B to C. All right, I've called it A. But I can also change bases from B to B tilde and C to C tilde. Now, I really want to know what is the corresponding transformation that I can apply to B tilde to get to C tilde that would give me the same thing as B between B and C. Okay, how do we keep those 2 things aligned? Can we solve that? Okay, and the answer is yes, we can. And the way we do that is by figuring out how to go from B tilde to B, then we apply A, and then we go from C to C tilde. And what that's done is that's given us the string of transformations. And again, we know we can string these matrix multiplications along. That gives us the same thing as going from B tilde to C tilde. That is the equivalent transformation in those change of bases. Okay. One thing to note here, and again, like maybe a small subtle difference, there are then another thing I don't like about the way the textbook phrases this. I don't like thinking of change of bases in terms of transformations. Okay. Reason being is now this becomes slightly confusing because what we were just doing over here is talking about the mapping from B to C as being a transformation, or C to B being a transformation, right? We were saying that transformation matrices change our basis. Transformations are a broader concept, Okay, and they share the notation here. Transformations are just these general A mappings. All right, and in that sense, you don't always need B and C to be the same dimension. Okay, but in that sense, this transformation isn't a change of basis. It's just a mapping that takes something in vector space B and gives me something else in vector space C. In fact, more often than not, what it will be is taking something in a 3D space to like a 2D space. And that's what A gives me, right? When we were solving those systems of linear equations last week, that's kind of what that A was doing. It was taking some X on the right and on the left and giving you a B on the right. Okay? They don't always have to be the same dimension. But a transformation, if you think of it just as a change of basis, it then becomes confusing because it has to keep the dimension the same to change bases, right? You have to be able to represent the same dimensional space every time. So note that in the slides here, on this exact slide where it starts speaking about basis changes, this A becomes implicitly a more general thing. It becomes any matrix multiplication that will take something from B and give me C. Okay? So the way I explain this and the way that I will kind of converse with you about it is that you have change of bases, which changes how you represent vectors in a space B or C. But the vectors themselves, those green, the line on the floor or that green vector from the earlier example, that does not change when I change my basis. But when I apply a transformation, the green vector itself is changing. Okay, that is the conceptual difference I make. That is how I square these concepts. And I can maybe draw it quickly just to make it clear. So I have some square space there. I have my green vector pointing off into the distance. I have my bases, and I'm just going to axis align it to make my life easy. Okay, I have my 3 basis vectors there. Okay, this green vector is represented as a set of coordinates, so let's call it ABC. Okay, what I can do is I can change my basis. I can rotate, I can stretch the blue vectors there however I want, and then my red things will change, right? They will have to adjust. Again, 1,000 meters, 1 kilometer, that kind of idea. But the green vector itself is staying the same. What this textbook is now talking about with a transformation matrix is some matrix A. Let's see if I can find a good color for this. Some matrix A. There we go. Can you guys see the yellow? Is that okay? No. All right. All right, that is now some matrix A, which is going to take me off of this space on the left and drop me into, let's call it 2 dimensions. Doesn't have to be 2 dimensions, can be whatever. Okay, and so now I have purple. Purple is going to drop me there. This green vector is going to now do something in this new space. All right, it will still have a basis in this new space. Okay, but this basis over here was B, and over here it's C. Now, obviously, and maybe the way I've drawn it doesn't, show this too much. We're drawing in 2D. But that green vector originally had A, B, C coordinates. It's now embedded in a 2D space. So it's just going to have, call it X, Y. Okay? Clearly, something has changed. So in terms of my language, okay, if I am doing something that keeps the green vector the same, it is a basis change, right? My coordinates might change, my basis will definitely change. Well, both will change. But then if I'm taking something that changes the green vector, that is a transformation. That is more of like what a neural network's doing. It's transforming something. The only case we have a neural network, for those who care, that is doing a change of basis is if you have something like an autoencoder going through a very large hidden layer. For any of you who know about like Claude, that is essentially what Claude is doing, this sparse autoencoder. It's learning how to get a very axis-aligned basis that represents the same thing as what's already in the data. But other than that, most times what a neural network is doing is the perspective is that it's actually transforming data. Okay, I hope that's clear. Again, I'm pedantic because it becomes very messy soon, but I respect the fact that it is 5 to 5 on a Friday. You'll have a tutorial for this to make sure you it clicks, and if it doesn't, you can ask me again. Okay, so we take the idea here is that I am going to, if I want to find the equivalent mapping between B tilde and C tilde, what's the first operation you would have to do? Well, I'm starting with a vector in B tilde, so I'm going to have to change my basis to B. So I'm going to apply that vector there, S. Okay? If B tilde is my new basis and B is my old basis, which mapping do we use, forward or backwards, on the basis itself? So B is my new basis, B tilde is my new basis, B is my old basis. I'm mapping from new to old bases vectors. Which change of basis matrix do I use? Forward or backwards? Backwards. There we go. Cool. So we're taking the backwards transformation there. Okay. I'm then essentially applying some transformation matrix A. All right. And then I'm going to change basis back. All right. But there is one somewhat more subtle point here. It's the fact that these transformations A are only going to ever be defined in terms of what they do to coordinates. Okay. And so what you guys said was correct. We were mapping from B tilde to B. So in the basis sense, we were using the backwards transform. But I want to act as if I'm working on coordinates. When we're talking about these equivalent transformations, we're always talking about the transformation acting on a coordinate. Okay. In which case, I'm talking about mapping from a coordinate in my new basis to a coordinate in my old basis. So I'm going to use the forward transform, the opposite of what I would have done on my basis itself. Okay? And that is why if you read these slides, what they're doing is applying S, my forward transform, my forward change of basis in the B space. Then I'm applying this transformation matrix, this A over there. And then I'm going, come on, and then I'm doing T inverse. And the fact that it's inverse in this case is just them kind of making that point that it is the change of basis from C to C tilde. So again, C basis is going from old to new, but we're talking in terms of coordinates. So we do the opposite. So it's now the coordinate in C is going to a coordinate in C tilde. Okay, so we're doing the backwards transform, which is why they have that inverse there. Okay, very long-winded, and if you don't do all four combinations, I think it can be tricky as to why that popped out there. Okay, and it can be tricky why A is now suddenly doing arbitrary things. Okay. To the earlier point, you can think of a change of basis as a transformation matrix, but then it is, I think, kind of you raised it. It's kind of similar to being a homomorphism. And so if you multiply something by the identity matrix, that's obviously, I'll come to you now, that's obviously still mapping to the same space, but changing nothing. But the identity matrix is a slightly more rigid concept than just mapping to the same space. Okay, so here S is the matrix, the basis change matrix that maps coordinates with respect to B tilde onto coordinates with respect to B. Again, the most important thing being that. Okay, and then T is the transformation or the basis change matrix that maps coordinates with respect to C tilde onto coordinates with respect to C. All right, what's your question?
No, just to double check. So when we were going from the B tilde to the original B,
yes,
in terms of bases, that was backwards
correct,
transformation, but the coordinates was forward.
Correct. Do you want to try C?
And then C with the bases we were going forward, but with the coordinates we were going backwards.
Correct. Here we go. And you just string those together. Nicely done. Yeah. Sure, you can forget that. And so here is the a very long-winded notation-y diagram of what we just did, right? So you can either just apply your new mapping to go from B tilde to C tilde, or you can map from B tilde to B, then use your mapping to C, and then come out after that, all right? And that'll give you your new solution. You can have a look at that. Okay, last slide, and it's a little bit of jargon, but it's going to come up when we do eigendecomposition and singular value decomposition. So there are equivalent mappings and there are similar mappings. Excuse me. An equivalent mapping, if we have now solved that problem, we got A tilde, then A and A tilde is an equivalent mapping to A if the S and the T are regular matrices so that they can be inverted, but they might be different dimensions, N and M, right? So remember I was saying to you that if A isn't, this transformation is more general, it might change the dimension, so it might go from N to M. But here these S's and T's, these are, as we just saw, our change of basis matrices, they must be square, right? Because they must be invertible to change bases, all right? And so in that case, now we say that A tilde and A are equivalent mappings in the different bases. If we are dealing in a situation where the mapping itself was also from N to N, okay, and this is again where I start to make that difference between a transformation is something that moves the green vector and doesn't just change my basis of how I represent it, but it's still moving my green vector into an n-dimensional space again, then it is called a similar mapping. Okay? So this is a more equivalent, just means they do the same thing in the two different bases. Similar means they do the same thing in the two different bases, but also don't change the embedding dimension. You're still in R3 if you start in R2. Okay, and that is the end of today's lecture. I know it was an intense one. This is, what I will say is this is the most intense lecture of the course. And so congratulations to you all for getting through that. It gets much, much easier from here because I imagine for a lot of you who've already seen singular value decomposition, that's looking really, really like familiar. That's looking a lot like an eigen decomposition. And so in like a month, once we've repeated these ideas a couple more times, this will become old hat. And you'll start to realize that singular value decomposition is actually a super intuitive thing.
With equivalence, does that mean that the basis can change? I mean, the dimensions can change?
Yeah, exactly. All right. Thank you, everyone. If no one has any questions, I'll stop the recording and I'll see you next week. Hopefully.